So what I'm going to talk about today is really how to apply IoT technologies to Industry 4.0 application. So I just briefly explain what ITRI is. I think some of you probably already know. So ITRI, think of it as sort of like a central research lab for all of the sort of companies in Taiwan. That was the original goal for setting up ITRI. And we have about 6,000 people and have many patents and have a lot of spin-offs. So it's quite successful over the years. So where I came from is information and communication research labs. So we focus on information, communication, electronics, and so on. We probably have about 1,100 staff members in that lab. So there are actually two sides of this story. One is the technology push, and the other is the demand pull, right? So right now, I just want to briefly talk about IoT. So by now, probably most of you are already familiar. I just want to review so that we are on the same page. So by IoT, I really mean that you put some sensors out there, go using some network, collect the sensor, analyze it, and react. Right? So this is the notion of you can sense, you can collect, you can analyze, and then you react. Think of it, this is almost like almost all the computer, communication, and electronic systems, we all design this way. So in terms of the underlying idea is pretty straightforward. There's nothing really new there, right? So, and yet sort of like almost like all the places that we go, all the seminars we go nowadays, they talk about IoT in one form or the other. So one example of IoT is, of course, intelligent building. Like suppose you want to build a modern building and you want to reduce the total power consumption. Then what you can do is you can embed various sensors to collect the occupancy information or weather or microclimate information, temperature, air quality throughout different corners of the building. And then now you can analyze it. And then you try to reconfigure the heating parameter, ventilation parameter, air conditioning parameter, or lighting to minimize the total energy consumption of that building. So looks to me pretty much like an example of IoT. And then, of course, we can apply the same idea to building as well as the entire electrical grid, and that's the notion of smart grid. So that's the technology push side. Now, from a demand pool side, why are we talking about Industry 4.0? One of the reasons is really the evolution of the economy, that the more and more people want sort of a wider diversity of product lines. They want more different types of products. And this figure shows that. This figure basically shows that, for this is a bunch of car company, the number of product, different type of product actually increases. And the average lifetime of each individual product shrinks, right? Just means that people want different variety. And they like new stuff, right? For whatever you have, they don't really like it for that long, right? That argues that the entire manufacturing sort of space needs to be revamped in order to accommodate this kind of need. So that's one thing. And the other is, of course, mass customization, right? Usually we talk about mass production, right? Everybody likes the same thing. So when we produce something, we produce 1 million, 10 million, a billion, and so on. That is a very nice thing from a manufacturing point of view, but that's not what users want. They want their personalized bicycle. They want their personalized shoes. And this is really not that unusual. In Taiwan, there are stores that actually build this personalized bicycle for you. They actually measure your body parameter and then try to fit the particular parameters, various configuration to you. Of course, that thing is pretty expensive, but there are demands for this kind of thing. So that's another trend of the society is going. And then, of course, from the sort of entire country's industrial development point of view, we want the sort of value add, the economic value added to the industry to be as big as possible, right? So here shows like 4 different countries: USA, Japan, Germany, Taiwan, and Korea, like 5 countries. And of course, these are the leading countries in the world. USA and Germany and Japan, they are much higher than Taiwan and Korea. And then if you want to increase your economic value added, you have no choice. You have to pursue those things that people feel valuable. And in some senses, it's a sort of somewhat niche and with a sort of higher profit margin. And then typically means customization of some sort. And that again stresses your manufacturing process. So all these things basically point to the direction that you need a very flexible manufacturing technology that can accommodate different degrees of customization so that you can maximize the value of the products. And that creates a new demand from a manufacturing point of view. And we are thinking maybe IoT can help fill that demand. Right? And that's why we have this today's talk about how to apply IoT technology to manufacturing. And Industry 4.0, for those of you who don't know what it is, right? From 1.0 basically means that the fact that you start to use this mechanical production equipment, right? You don't use animals or humans to producing anymore. You use some kind of mechanical production equipment, like driven by engine of some kind. And the second evolution is, of course, the invention of this mass production, like the Ford, the Model T, like the division of labor concept. And then the use of electrical energy, not just a mechanical energy, but also electrical energy. Now, the third revolution is the use of IT and electronics to automate the production process. Just because you automate the production process, you use this numerical control machine to cut things. So you don't really just use a manually control machining tool to cut things anymore. You use IT or electronics to automate that process. But just because you can automate that process doesn't mean that process is optimized. The optimization comes to the fourth. The 4.0 is about optimize that manufacturing process. And that manufacturing process can be very easily reconfigurable on the fly so they can accommodate this mass production customization trend that I just talked about. And the idea there is, of course, the typical thing that we know about IoT. You embed these sensors into the manufacturing process. You collect that sensor data, you analyze it, and then you can use this information to optimize, to reconfigure your manufacturing process in real time. Right? So that's the idea of Industry 4.0. So one canonical example of 4.0 is, of course, that's almost a well-known example, Siemens' smart plant in Hamburg. So it has I just basically read out this parameter, 950 production lines using 1.6 billion component combination coming from this many suppliers. And it can reconfigure manufacturing process in 24 hours with an error rate of 10 ppm, 10 parts per million, right? For every million components it produces, fewer than 10 elements are error. Right? And then over 20 years, this space doesn't change. The number of people doesn't change, and it achieved 6 times improvement in productivity just by using various forms of that IoT technology that I alluded to. So if you think about it, to do this, we can lay out sort of like explicitly lay out a set of technology required to build Industry 4.0 manufacturing plant. You need some sort of sensor, right? You need to embed some sensors for what? For manufacturing equipment and for work pieces. So when we embed sensor, what exactly are we using these sensors for? We are measuring something. So what are we measuring? We are measuring those manufacturing equipment, as well as the things that we produce. That's the notion of work pieces, right? So we are measuring these two things. So work pieces, like, we already have some idea that if it's a perfect manufacturing process, it should be like that. But in fact, it isn't like that. So we want to know the difference between should be and turn out to be. So that's the error, or that's the imperfection between the idea and the practice. And then for manufacturing process equipment, we want to know how healthy it is and its operation condition. Is it doing what it is supposed to do? Dr.Tzi-Cker Chiueh just mentioned about using simulation in your manufacturing process. So we already know ideally this manufacturing equipment should behave like this, but in practice they don't. And the difference is because we are measuring them. So we want to know whether they are working as well as they should. And then once we have this sensor, of course, we need to communicate them back, collect them, and then store them in some form. And then finally, we have to do some data analysis, and based on the results of the analysis, we'll do something to the manufacturing process. Now, when we do analysis, there are actually 2 types of analysis we can do. One is that if we already have a very clear idea of the manufacturing process, we know exactly the physics and math involved in this manufacturing process. In other words, we have a complete and accurate simulation model of the manufacturing process, which is very rare because people don't do that. But if we have that, then we can do model-based. Then we have a simulation model. Then I have this feedback. Then I can adjust using this model to predict what's going to happen. And that's the notion of cyber-physical system. Cyber means virtual. There's a simulation model in the cyberspace, and you correspond them with the physical measurement that you get, right? And this tells you that what you are supposed to do to tune your manufacturing process. In practice, you don't have this. You probably have a partial model. So whatever is missing that you cannot do, the only thing you can go by is statistics. You have to learn from history. And that's where big data, machine learning, and AI comes in. Right? So in practice, it's a combination of these two techniques that actually get used in practice. So, but then in Taiwan in particular, I'm sure that in Thailand the same thing, and probably to some extent in Japan as well, that a lot of these companies are small and medium enterprise. They don't really know much about like a simulation model or big data or AI. Even if they do, they have to hire people to do this kind of programming, and they cannot afford it. That's at least in Taiwan. If I'm a very qualified computer science major, I'm not going to go to any manufacturing plant to write program for them. I'm going to go to Google. Why would I want to write program for this guy? I would do something else. That's like a better use of my time. So we recognize this, that the manufacturing sector is not very suited for high-quality programmers. So when you design your IoT system, your industrial IoT system, you have to assume that these guys do not have high-quality programmers to write this application or software for them. So the only way to do it is that you have to simplify the process of developing this industrial IoT application. So like I said, they cannot afford a programmer to build this industrial IoT application, and even if they can, they cannot, it's difficult to recruit them. So we want to build this industrial IoT path to reduce the development effort and to reduce the operation control, support overhead. Right? So that's why we need some sort of infrastructure to help facilitate the development of this industrial IoT application. Now, one of the problems in this industrial IoT system is the fact that in real manufacturing plant, they use various kinds of network. At the physical layer, at the layer 2, at the layer 3, and even at the information model. Like you have various kinds of wired or wireless technology, or more proprietary motors or PLC or field bus and so on. And you need to somehow have a way to deal with them. Okay, it's not an impossible task, it's just messy. Okay, so it's not like technically it's that challenging, but somebody has to do it. More problematically is that you need to do some sort of translation. Like down below, you probably have different kinds of manufacturing equipment coming from maybe Japan, Germany, Italy, Taiwan, Korea, and so on. And there's no unified standard of speaking out of various kinds of sensors data and so on. So you need to do some sort of translation. And then once you translate it into some kind of common language, then you have to somehow doing some sort of conversion into the unified unit, abstract all the details out into some common information model. And there you also need to worry about some sort of security. So that's why we put a threat detection here. And once you have that, now you have information expressed in common form, but not all the information need to go back to the cloud, go to the back end. So we do some sort of information filtering to cut down the unnecessary data and only relay all the most important data back. And once we do that, we also do some kind of information aggregation. Like probably for certain piece of sensor data, it doesn't make sense to send back every second. It's very okay to send this kind of information in aggregate form every minute, for example. So that's what we mean by information aggregation. And then finally, we have to do encryption, and so that you can send back to the backend. So that's what we call like in the networking and communication aspect of an industrial IoT platform that you need to solve the network, sensor networking and communication problem. And then in terms of the path itself, once you get this information from various manufacturing equipment or from the various work pieces, then what do? First thing is that you have to do real-time collection, filtering, indexing, and storage. So this information, you have to put it somewhere, right, into some sort of database. And then you present an API for upper layer application to do data access query and to provide some kind of simple visualization. You can show some simple trend or to show some anomaly, standard deviation, and so on. So this is what we call basic data analysis, including trending, anomaly, and alerting. All these things will be done by parts. We don't want to bother this, industrial IoT SaaS developer to do these more mundane things. And then on top, you have various kinds of SaaS, this application. They either using what I call CPS, Cyber Physical System Model-based analysis, or they do big data-based analysis, or they manually analyze them. Okay. And then once we do all the analysis, then we have another component called software-defined manufacturing process, which I'm going to talk about next. Now we want to go through this process to reconfigure your manufacturing or production process. And then along the way, then when you develop this, this path also provide continuous integration of IIoT SaaS testing. Because this is an industrial production process, so we need the quality of the software to be really high, right? You don't really want to have a lot of bugs and then stop the manufacturing process in the middle. So you really need to have a good software testing methodology. And the PaaS also provides unified log analysis for operational support, for device management, and so on. And then this is what we call sort of a standard IIoT application. Can coexist with all the more traditional manufacturing execution system or this supply chain management system on the right? So this is the part that we want to focus on, more real-time optimization of the manufacturing process as opposed to sort of slower time scale of manufacturing execution or even like an order processing, kind of more supply chain kind of management system. And last slides, I talk about this notion of software-defined manufacturing process. If you are in the IT space nowadays, everybody is talking about software-defined, like software-defined storage, software-defined networking, or software-defined data center, software-defined server, this and that. Now, we want to apply that idea in manufacturing process. So what do we mean? Like, you can think of a manufacturing process consists of a bunch of manufacturing equipment, right? And if you can change the personality or the soul of this manufacturing equipment, then you can define a new manufacturing process. So the same set of manufacturing hardware or equipment, just by changing their configuration or their control program, now you can redefine what this particular manufacturing line of manufacturing equipment can do. And that's what we mean by software defined. And why do we want to do that? Because we want to accommodate this large variety, small volume manufacturing. Like people just want your personalized shoe. The entire world only need one. That's what it means by personalized shoe. Only one guy wants it. And we want a manufacturing process that can accommodate that. Right? So you need a way to reconfigure your manufacturing process really quickly and reliably. So by that we mean that a manufacturing process really consists of the hardware, equipment, plus recipe, the things that go into the equipment. And recipe means the configuration parameter and the control program that runs in the manufacturing equipment, like G-code for machining tool or control program for robot, for example. So just like the typical software-defined, we have a central software-defined manufacturing process controller that can maintain various recipes. And then once you want to change your manufacturing line to do something else, all you have to do is just upload a different recipe in a consistent, reliable, and error-free fashion. And then you could do all the other things. And that's what we mean. That's another way to look at this new form of manufacturing, is to look at it like you can completely separate the manufacturing equipment and their recipe. And then you can do this in a consistent and error-free fashion. And then, of course, you want to provide some sort of visualizations for, like I say, basic trending, basic bar, histogram, this and that, so that you can simplify. You want to remove this kind of task from typical industrial IoT application developer. They don't have to do this. The PaaS system should be able to do this basic trending and data analysis job. And like I said, that in manufacturing event analysis, the first number one thing is that you have to have a way to uniquely identify each work piece, each equipment, right? And what you want to do is that for every manufacturing object, like either it's an equipment or a work piece, you want to know, in particular work piece, you want to know the sequence of manufacturing steps that it goes through. So imagine that you are talking about a shoe, let's say, or laptop, for example. For a laptop, I want to uniquely identify each laptop that I manufacture. And I want to know the sequence of manufacturing steps that it goes through. It goes through which set of manufacturing equipment. And then you do quality check after each manufacturing step. And so for when we say each manufacturing step, we mean the parameter and the health status of those manufacturing equipment. So now I have the complete manufacturing resume for that particular work piece. I know which manufacturing equipment it goes through, and I know the status and the parameter used in each of the manufacturing equipment. And that constitutes a complete resume for that work piece. And from there, I can do various kind of analysis. For example, I can do root cause analysis. Like for a particular lot, the yield is not high, then I can go back and check, like what's the problem? Like whether there's some manufacturing equipment that are misconfigured, or there's a certain environmental factor that contribute to that low yield. And then we distinguish this manufacturing event analysis into two types. One is the basic type, one is the deep type. The basic type is sort of application independent, and the deep type is application dependent, right? So application independent could be just simple, shallow analysis, and application dependent is deep. There you really use more advanced AI or machine learning technology to do it. And then in order to develop an IIoT system, then you need to go through this process. I don't want to spend time doing this, but this basically just shows that if you use our IIoT parts, all you need to do is the red part. All the black parts are already taken care of by the IIoT parts system. So as a developer that uses our IIoT parts system, you only need to focus on the red parts of developing an IIoT system. And Dr.Tzi-Cker Chiueh already talked about this big data analysis, so I'm not going to go into that. There are various technologies that you can use, and you probably use this to do root cause analysis or to find various kind of correlation, or you want to do equipment failure prediction, this and that. So there are many different applications. And from our understanding, you need to apply different type of technology for different type of big data analysis technology for different kinds of problems. And then the other thing is a cyber-physical system. That's why I'm just saying that, like, if you already somehow you can create a complete and accurate simulation model of your manufacturing process, then you go by this particular route. So like I say, you have a digital simulation model of the manufacturing process. And then you can use a measure manufacturing error, right? You have a work piece, and what it should be and what it turned out to be, that error. You can using that measure the manufacturing errors to fine-tune your digital model, and then use to control manufacturing equipment and the workpiece design in real time. So I'm going to give you an example just in a minute. Right? So this is the idea. Like once you have a simulation model, and now you know that whatever you produce is not exactly according to the theory. So that's the error. And then you can go back and check, what do I do? Maybe my simulation model is not that great, or maybe I need to change my input design so that I can sort of get around the imperfection of the manufacturing process. And this is the comparison of commercial IoT parts system, and the kind. So there are various kind of commercial system out there doing various kind of things, but none of them are really that geared toward this Industry 4.0 industrial IoT system just yet, at least not with the same types of functionality that I just introduced. And this is Siemens' solution for Industry 4.0. I think the most important concept is that whatever I talked about today is really about manufacturing, but Siemens has a broader view. It talks about product design and then production planning, that's the process design. Like you create a product, so you probably have a CAD model of that product. And in order to manufacture that product, you create the manufacturing process, you design that, and hopefully you have a simulation model for that. And now at the runtime, you run it and see whether that simulation model actually is that accurate. And if it's indeed accurate, then you can use it to fine-tune your real-world manufacturing process, and so on. And so that's what it calls product life cycle management. So it has a broader view than what I'm talking about. I focus mainly on manufacturing process optimization. So in the following 3 slides, I'm going to give you some examples of what some of the applications that we have been working on in the last 12 months. The first one is about machining tool. So in the beginning, we are cutting something. So we first introduce some kind of online measurement. So just to this online measurement is basically insertion of some sensors, right? So we want to know maybe this is a machining tool and it has some knife to cut something. And we want to know this knife is vibrating or not. If this knife is vibrating, then whatever it cuts is not going to be very accurate, right? So I need to know whether the knife of this machining tool is very, very stable. So I need to introduction of some kind of sensor to calibrate that. And once I have that, then I can do measurement of the sound, vibration, or temperature to measure this kind of information. And then at the same time, I can do manufacturing defect monitoring. So whatever I produce, I cut something, right? And this thing is supposed to be an error of whatever, 1 centimeter, and it turns out the error is 1.2 centimeter. Then what? So now this error will feed back to me, then I'll create a cut path compensation. And that's what I mean by using some kind of simulation model to adjust the physical manufacturing process. So for example, I already know that this knife is vibrating. Then I'm asking myself, how do I configure this machining tool parameter such that I can compensate for this kind of vibration? And in the end, the produced result, the workpiece, the error is minimized, right? So that's because I already know how much it vibrates, and I have some idea that when it vibrates this much, it will produce this kind of error in the workpiece. And then I say, maybe I should tune that configuration or control parameter of that machining tool. Then I can reduce the impact of that vibration so that I can cut down the error in the workpiece. So that's one example of using this entire feedback to do it. The other example is similar. It's a high precision PCB production, PC board production. So there, for example, we are doing exposure, right? So when you have a really high resolution PCB board that you are producing, and you have to expose them so that you can inch their sort of the signal path and so on. And when you do this, it turns out that when you expose them, the thing that you produce is not exactly perfect. The thing tends to be warped because of the temperature. It gets heated, for example. So the thing is not exactly straight and so on. So there is some form of warpage. And in order to do that, so I need to measure the degree of warpage of the physical manufacturing process. And then this information will go back to the design. Then I ask, I already have a PCB design file, Gerber file, and I know that this manufacturing process is not perfect. It will result in some form of warpage. Things will get twisted a little bit. Then I say, well, how do I modify this input PCB file such that even this manufacturing process has this warpage effect, the resulting PCB has to be the same as what I started with. All right. And that's the idea of feedback, right? First, I measure how imperfect this physical manufacturing process. And I take that thing and go back to modify my input, such that even when you go through this imperfect manufacturing process, the resulting product is as perfect as it can be, all right? And that's what we are doing. So I need to measure, I need to analyze, and then I need to modify the input so that I can get through this, the imperfection in the real world manufacturing process. The third example is again related to machining tool, but it's a somewhat different angle. So Taiwan is the world's number 4, has a world's number 4 machining tool industry. So we always want to upgrade ourselves. And it turns out that if you want to upgrade, then you cannot go for this sort of like more mass kind of market. You have to go to this sort of more high-end user. And for high-end user, the number one requirement is you have to have a very high-quality production support. So I sell you something, right? And then I have to have some kind of production support that can support you. Once you have a problem, in 24 hours or in 12 hours, I can support you. So we want to use this Industry 4.0 or industrial IoT technology to facilitate the product support of high-end machining tools. In other words, whenever we sell a machining tools to some high-value customer, we already embed a bunch of sensors inside the machining tool. So constantly, we are watching how healthy these machining tools are. And some of the components, when they are going to fail, and before they even fail, we already ship the components to them. So the disruption to their production run is minimized. Because I already know this particular key component is going to fail in 1 week. So beforehand, I already ship the component to them, and I tell them that you probably need to replace the component beforehand, so your disruption is like 2 hours, for example. As opposed to today, out of the blue, your users find out that there's certain component in the machining tool fail, and the entire manufacturing process have to shut down, for example. And so you can use this thing to do things like proactive equipment component replacement, right? Before they know it, I already tell you that it's going to fail, and I'm going to ship that component to you. And we can do real-time diagnosis and maintenance, and we can do technical consulting service. In many cases, the users of this machining tool do not really know how to use it. And the guy who sells the machining tool can tell them, providing consulting service for them. And then periodic software upgrade and so on. This particular model is not our invention. Like Japan's Mazak and Germany's DMG are doing this for a long time. They are starting to do this sort of proactive product support using remote monitoring and analysis. So this is my last slide. So I think what's known as Industry 4.0 is nothing but an application of IoT technology to improve manufacturing process efficiency and quality. And the reason we need to do that is what I just said. You want to increase the value, then you need to have the ability to accommodate mass customization. People just want different things. So each slot is going to be small. And that means your manufacturing process has to be very flexible. At the same time, you cannot compromise the quality. The quality should stay the same. So basic idea, sense, analyze, and control. And of course, different manufacturing domain will require different sensor data analysis. And like I say, if you have a model, that's fine, that's great. But most people don't have model. So that's why you rely on statistics. And there you use big data, machine learning, or AI. And the final point I want to stress is that not only the idea is fine, you have to worry about, that's our experiences. Like, all these ideas are nice, except in practice, those guys, small and medium manufacturers, they just cannot hire enough programmers to help them. They just don't have computer science major. They probably have whatever, physics major or whatever major they turn into computer science. They just don't have computer science people that can help them. So that's a practical problem. We know in theory, there's nothing, I have this IoT and you find some computer science people doing big data analysis, this problem is solved, except they cannot hire. They cannot afford or they cannot attract this kind of people. So that's a practical implementation problem. If a country wants to push this Industry 4.0, they have to solve this problem, right? And that at least is our experience. So how do we solve the problem that programmers are hard to come by the manufacturing sector problem? And that's another sort of more practical implementation aspect that Taiwan start to find out, and I'm sure that this is probably something that Thailand probably will find as well. Thank you.